Hi everyone and welcome back. We'll continue our investigation and exploration about data in C++ from the fourth topic, which is dynamic allocation. In C++ or any other programming languages, you have at least two types of memory that you can store your data: stack memory and heap memory. First of all, don't confuse a stack memory with a stack data structure, or don't confuse heap memory with heap data structure. We have a stack is the term is similar, but we are using that in two different contexts. So although we are using the same term, but they are not related, and you should not confuse them. All right. In any programming languages, we have at least two options for storing the data. On a stack, everything that any variable that you were creating so far was created on a stack memory. But right now, we will use dynamic allocation. Dynamic allocation means using heap memory to store your data. And there are some differences between a stack and heap. Stack memory, all the variables on the stack memory are dynamically destroyed. They will be dynamically destroyed when you get out of the scope. You remember when we were discussing scope levels, I explained that when we declare an integer inside a block and we get out of that block, the integer will get automatically destroyed. But it's not the case for dynamically allocated memory, dynamically allocated variables. But as usual, let's consider this topic, let's explore this topic in three steps. First, the concept, and then necessity, and then syntax. The concept should be clear so far. We have two different types and two different types of memory, stack and heap, and they have different features. The necessity of using heap is a larger memory than a stack, but a stack is faster. And the next reason that we need to dynamically allocate that is about the size. Like when you write your program, you might allocate a certain amount of block for your array, but when you are running your program, based on the input that you get from your user, your requirements might change, and you might need a larger part of a larger block of memory for storing your data. And in that case, you cannot access more stack memory when you are in a runtime. You can use heap to get a larger block of memory and store your data, whatever it is on that block of memory in heap. So this is the necessity. Pretty much it boils down to the amount of and the space that we have. We have a lot of space in heap, but limited in a stack. And the syntax, right now I will go to the syntax, but before getting into the syntax, bear this important difference between them in mind, that a stack, any variable on a stack, they will be automatically destroyed when you get out of the scope, but it is not the case for heap. And any data that you have on the heap, it is up to you to deallocate that space in your heap memory to when you don't need that data anymore. Otherwise, your memory will eat up all the space in heap, and you get and your program will crash. So it is up to you to deallocate the space that you got on heap. All right. We had different types of data. We had user-defined data type, and we have built-in data type and derived data types. Right now in this notebook we will more or less cover all of them to see how can we dynamically allocate different data types. We start with primitive data types like integer, float, char, and boolean. This line 48. First, let's start with the right side of the equation. New is the keyword that we can dynamically allocate space for our variable, for our data on a heap memory. So I'm using new here to get enough space for storing one integer, and the value that I'm storing in this integer is 7. So let's see what will happen if you execute the right side of the equation. New means I need a memory, I need a block on heap, and int means I need 4 bytes because int occupies 4 bytes on your memory, and 7 means store 7. So when you use 7 compiler, new int 7 compiler come to the heapest memory and check if we have any available space or not. The compiler says that we have 4 bytes available here. So the compiler will reserve this space for you and return the address. And you already know what is address. Any block of memory in a stack or heap has a unique address. So it will return this address for you and store 7 as a value. And on the left side of this assignment, we have int star IPTR, which means IPTR is a pointer that is pointing to an integer. And I am storing the address of int new 7 into this pointer. So IPTR is a normal variable, it's not dynamically allocated. It is on a stack. It has its own address, IPTR. It has its own address, and it has its value, and its value is the address of the memory block that we reserved on the heap, and we stored 7 in that. All right, so right now by using new int 7, we got one memory block on the heap and we stored that value. I will right now use IPTR to print that. Let me comment out the other parts. All right. By using new int 7, we got one memory block and we stored 7 and the value is 7. The value is 7 and then, but okay, let's go back to the diagram. When you are done with using this block of memory, it is the programmer's responsibility to free this block of memory, to free this up. The way that you can free this up is by using delete keyword and then passing the address of that block of memory on heap that you want to free that up. All right, by running this line, we deleted this block of memory, so we no longer have anything in this block. It is freed up. Other part of your code can reserve this block for other purposes, but the thing is, it is no longer occupied by our new int 7 variable, by our 7 data. All right, another case It's a very important case, as we usually have this in programming and we have to be careful about that. Is I have one pointer here that is pointing to integer, and I'm dynamically allocating one block of memory for storing 8 on the heap. And I'm storing, and I will store the address of 8 in IPTR2. Alright, and next I will decide to store another, I will decide to get another block of memory on heap, and instead of address of 8 I will store the address of 9. So right now I have the address of 9 in IPTR2, and when I delete IPTR2, it will compiler goes and delete this block of memory, block of 9. But the thing is, I no longer have any sort of access whatsoever to 8 value on the heap, and the address is lost, and there is no way for me to restore that address, because I simply change the address to another value, and I no longer have any access to the address of 8. So this is called memory leakage. And if you have many memory leakage in your program, chances are you get out of heap space and your program will crash. So you should be aware of this problem and manually delete all of the spaces that you reserved on the heap memory when you no longer have any when you no longer need these variables. All right, so and one way that we can prevent this issue is, first, before storing another address in IPTR2, we need to delete this block of memory that IPTR is pointing to, and then storing another value. Let me run the code. Yeah. All right. This is how we can dynamically allocate a block of memory for primitive data types like int, float, char, and boolean. And other data types are the same. You can simply change this int to another data type like float, double, char, bool. The second part is user-defined types. Almost all the times we don't need to dynamically allocate a block of memory for enum or union. And also dynamically allocating a space for a structure is pretty much the same as a class. So here I have a class named the student. It has two public functions, print info, which will print ID and GPA, and also it has another function, set ID and GPA. Syntax is not complicated, similar to the primitive data type. First I need a pointer because I have to store the address returned by this statement, and by new student parentheses I will go to the heap and see if I have enough space for storing one object of a class student, and then I will return the address. And you already know from the previous videos that if you have a pointer to a class, if you have a pointer to an object, you need to use arrow for getting access to their public attributes or public functions. So A student with ID -1 has a GPA 4. These are the default values printed because of this statement that we have here. And then when I'm done with this variable, with this student variable that I have on the heap memory, I have to free that up with delete keyword. All right, this is the second part. We covered user-defined types, and the third part, let me uncomment. Why I keep saying unblock instead of uncomment? I don't know. Anyways, all right, I uncommented part 3, and then right now we'll discuss dynamically allocating a pointer. This is an interesting case. Like, first on the stack, I have int star p. So here I have a variable called p, which is a pointer to a pointer. It has its own address and a value, but its value is an address of another pointer that is on the heap. This is a pointer. New int star returns a pointer. At first it declares a pointer, it creates a pointer on the heap, and then returns its address. So we don't have any name for this block of memory, for this pointer to an integer on the heap, but we have its address, and that is enough. That is everything that we need. We don't need its name. And okay, and then with star p, when you use a star p, when you use this star, you dereference p, which is a pointer to a pointer, one time. So by using a star p, you will come to this block of memory. So star p refers to this pointer that we have here. And then I'm storing, let's discuss the right side of the assignment first. New int 5. We'll go to the heap and find the space, store 5, and return its address. But the returned address will be stored in the star p in this pointer. Okay, so right now we have a chain. P, if we start from P and dereference that one time, which means if we write star P, we will go to this pointer, and if we dereference that one more time from this pointer, we will go to the final data, which is the integer 5. Okay, let's run the code and see the result. The address stored in the first pointer is this address, and the address stored in the second pointer is star p. The address stored in the second pointer. All right, okay. I thought both of them are the same, but no, they are not the same. Look, we have C8, and the second address is D8. Okay, so here the address stored in the first pointer is C8, and the address stored the address stored here is D8. D8 is referring to this block of memory. Okay, by C8 we will go to the second pointer, and by D8 we will come here, the last part of the chain. And the value stored in the memory block at the second pointer is that is pointing to it is star star p, which is 5. All right, the interesting part of the discussion, which is deallocation. First, you need to deallocate this block of memory by passing its address, which is stored in star p, and then you have to deallocate this pointer that is on the heap. So this is how we can free up those block of memories. Alright, right now we know how to dynamically allocate a pointer. The second case is dynamically allocating an array or a 1D array. Number of elements, I have one variable for that, and then let's discuss the right side first. New int square brackets. Square brackets, and don't confuse this parentheses with the square brackets. When you use a square bracket, you are getting an array on the heap. But when you are using this parentheses, you only get one single number. So int parentheses, new int parentheses will reserve one block of memory for you for storing one single integer. But new int square brackets will reserve an array for you, three blocks for storing 3 integers. And the value that's alright, so let's go to the diagram. So when you use new int square brackets 3, compiler goes and find 3 contiguous block three blocks for you for storing the 3 integers that you have, because the size of your array is 3, and then it will return the address of the first block for you. And then we can store that in 1D array pointer. It's a pointer. Alright, but by this line, I'm initializing the elements in my array, and notice that I'm using the pointer's name here instead of new int, because I don't have the name of that, but I have the pointer that is pointing to that array. So I'm using 1D array name here with this square brackets and changing its value to 21. It should have been j plus 1, but it doesn't matter anyways. All right. So by this for loop, I will initialize the dynamically allocated array, and then I will print the numbers. As you can see, the numbers are 2021 and 2022. Value plus plus. First, we store the value. I hope that you remember the plus plus operator. When we have this statement, first we assign the value of this value variable to our 1D array, the jth element, and then we increment the value. We increment this value variable, and that's why we have 20 at the beginning, and then it will be 21, and the last element is 22 because of this plus plus operator. All right. And the most important part is you have to deallocate the memory that you got. And the way that you can deallocate a 1D array, an array, is by delete a square bracket operator. Delete keyword, and then you have to write square brackets and then the name of the pointer that is referring to that block of memory. And the second case, which is very interesting and useful, is and frequently used, is dynamically allocating a 2D array. And by the way, there are some references here. If you have any question, please check them out. For instance, stack versus heap, the differences, and reference to a dynamic memory. Here we only have pointer to a dynamic memory. We didn't discuss reference to a dynamic memory. You can definitely find more insights by reading these web pages, but anyways, let's go back to the last part, which is dynamically allocating the 2D array. Alrighty, imagine this is our 2D array. 1, 2, 3, 4. And the first line, the first row is one array, and the second row is another array. And then we want to dynamically allocate a space for our 2D array. The way that we can do that is by having a pointer to a pointer first, which is pointing to an array of pointers, P1 and P2. So P0 is a pointer to a array of pointers, and the elements of this array are pointers, and we need to have 2 pointers in this array because we have 2 rows, and this P1 is pointing to the first row, and this P2 is pointing to the second row. So how can we access having P0, having P, let's call it P, let me remove this index. Having P, how can we get access to the first element, the one element in our 2D array? The element at row 1, at row 0, and at column 0. How can we get access to that? First, we need to get access to P1, all right? So P square brackets 0. will give us the P1, and then we will, from P1 we will go to the first element of this P1 in this array that P1 is pointing. This is the array that P1 is pointing. So we will go to the first element in this array, which is of the index of 0. And what if we want to change the value of 2 to, for instance, 5? We need to change we still need P1 pointer by using P square bracket 0, and then from P0 we need to go to the second element in our array, in our first row, by using 1, and we change that, for instance, to any number that we want, 5. So this is the concept behind pointer to a pointer to a 2D array that is dynamically allocated. We will see how we will see the syntax, but first we need to understand the concept. Then the necessity is obvious. We usually need 2D arrays in the programming, and when we are, especially when we have a large 2D array, and we need, in that case we need to store that on the heap memory. So we need the dynamic allocation. All right, the last part is syntax. Let's go to the syntax. As I said, we need a pointer to a pointer, and that pointer needs to, and we need to allocate an array of pointers that are pointing to integer. This is how we can reserve an array of pointers to integer by using new int a star and then a square brackets, and then the size of pointers that we have, the row size, the number of rows that we have. And then again here, for instance, for P0 we need to allocate a space on memory to store this row. This is not a array of pointers anymore. It is an array of integers. All right, so that's why we have new int without any star. So this is how we do the allocation. The next part is assigning value. We use the first pointer to pointers and then use the square brackets, row number and column number to change the value. And if we start from the 0, the first row would be 1 up to 7. Why 7? Because we have 7 columns. And then next row starts with 8, ends with 14, and so on and so forth. So we are done with the memory allocation. Sorry, we are done with the assigning the values. Then we print them with a nested for loop. And the deallocation. All right. First, you need to deallocate all of these blocks, all of these rows. First, you need to deallocate all of these, and then once you are done with all of them, you need to deallocate these pointers. I guess you already know why we need to start from the last part for the deallocation. Because if you deallocate these pointers first, you no longer have access to this array of numbers. So you need to start from the last part, deallocate them, and go to the first pointer that we have. But bear in mind that we don't need to deallocate P itself. When you write delete square brackets a, it will deallocate all of these pointers that we have. But we don't deallocate this P. Do you know why? Can you guess the reason? Can you pause the video and guess the reason? All right, the reason is P, or A in our case, is not dynamically allocated. It is a regular variable on a stack, and it will be automatically deallocated, and you don't need to worry about that. Alright, that was a pretty long tutorial. Hope you understood everything and enjoyed, and take care. See you later.